So I was telling you that in terms of EK diagram, this information of valence band and conduction band can be shown like this. This upper EK diagram, it represents the conduction band. In the lower EK diagram, it represents the valence band. And the blue circles, they represent the filled states by the electrons, and here the yellow circles, they represent the empty states. So if we have a suitable energy, if we have a suitable light of suitable energy which is greater than or equal to the band gap for this semiconductor, then the electrons can be excited from the valence band to the conduction band, and we will have the equal number of generation of electron hole pair. So here the two EK diagram look like the same, but actually they are not the same in real semiconductors. For example, in case of gallium arsenide semiconductor, this EK diagram is very sharp, very narrow, and the conduction band is very broad. That's why the mobility of electron in case of gallium arsenide semiconductor is very high. But because the valence band is very broad, so the mobility is very small. So EK diagram defines the effective mass, and effective mass decides the mobility like this. So I told you about direct and indirect band semiconductor. So the first diagram here is for the gallium arsenide semiconductor, and you can see how sharp the conduction band is in comparison to the valence band. Valence band is very broad. So if the top of the valence band and the bottom of the conduction band, they lie at the same K value. Remember, the horizontal axis is the K wave vector. So if the top of the valence band and the bottom of conduction band, they are at the same K value, then the electron can jump from the conduction band to the valence band, and it will annihilate the hole. One electron hole pair will be lost, and the difference of the energy would be emitted in the form of light or in the form of a photon. So such materials where the top of valence band and bottom of conduction band, they are at the same K value, they are known as the direct band semiconductors, and they are used for making light emitting devices like LED, like semiconductor lasers. On the other hand, if the top of valence band is not matching with the bottom of conduction band, you can see here they are at the different K value. This electron cannot obliquely jump from here to here because there will be a large difference in momentum, and in order to conserve the momentum, this electron cannot directly jump from here to here. But this electron, first it will go to an impurity site that is represented by ER, and there will be emission of a phonon, not photon. And if you recall, phonons are the lattice vibrations, thermal vibrations. And then this electron will jump from this recombination center to the valence band, and electron hole pair will be annihilated, but with the emission of a phonon. So in indirect band semiconductor, phonons are generated, means material is heated up, not we don't have the emission of photons. So indirect band materials are not used for making light emitting devices. So silicon is not used in making light emitting devices. Only direct band semiconductors are used. This is very important question for interview. You must remember it. So I was telling you before the net got interrupted, the formation of a PN junction. Here in this diagram we have P semiconductor and N semiconductor. You know that these white circles, they represent the boron ions, negatively charged ions, and associated with each boron ion we have a hole. we have a hole. Similarly, on the N side, we have the red circles with plus sign. They represent arsenic plus ion. And with every arsenic plus ion, we have one electron associated. So on the P side, we have holes as the majority carriers, electrons as the minority carrier. On the N side, we have electrons as the majority carriers and holes as the minority carriers. Now, as the junction forms, which is known as the metallurgical junction, there is a concentration gradient. On the P side, we have large number of holes. On the N side, we have less number of holes. So holes will start diffusing from P side to N side. Similarly, we have on the N side large number of holes, and on P side less number of electrons. So electrons will start diffusing from N side to P side. And due to this diffusion of majority carriers, there will be a region around the metallurgical junction which will be depleted of free charge carriers. That's why it is known as depletion layer. Other name is space charge layer. Because we have only the immobile ions which cannot move. So there will be a built-in electric field that will point from positive to negative. So you can see an electric field is represented by an arrow which points from N side to P side, and it is shown by EO. The width of this depletion layer on the P side is denoted by WP, and on N side it is denoted by WN. So total width of the depletion layer is W. Now on this graph we can show on a semi-low graph the concentration of holes and electrons. On the P side, holes are the majority carrier, their number is large, that's why it is large here, P naught. It represents the whole concentration on P side under thermal equilibrium. And as we go, as we move through the space charge region and go to the N region, the hole becomes minority carrier. Their number is small, P N naught. Hole concentration on N side under thermal equilibrium. Similarly, the blue line, it represents the hole, the electron on P side under thermal equilibrium. This number is very less. As it goes through the depletion layer, and electrons on N side become majority carrier, N naught, electron concentration of N side. But their product is still equal to Ni square. This mass action law is still followed. If we plot the charge density across the depletion layer, because we have on the P side negatively charged, so it is shown by this circle E minus Na that encloses all these negative charge. On the P side we have positive arsenic ions, so that's why they have this positively charged concentration. So if we integrate using the Maxwell first equation, if we integrate the charge density, then we will get the electric field. And if we plot it, the electric field profile across the depletion layer would be like this. It would be like this. And from the electric field, we can calculate the electric potential. If we integrate this green triangle, we will get the parabola. And from the potential, we can calculate the potential energy by multiplying it with charge. Hole has positive charge, so it will be like this. And for electron, the potential energy across the depletion layer will vary like this. So these are the expressions for electric field, built-in electric field. It is given by E minus E Nd Wn divided by the dielectric constant. Built-in voltage is given as V naught is equal to kBt upon E ln Na Nd upon Ni square, and the width of depletion layer is given by this formula. We can also relate the concentration of hole on P side to the concentration of hole on N side through these relations. P N naught divided by P naught is equal to exponential minus EV upon kBt. Similarly, we can denote the concentration of electron on p side to the concentration of concentration of electron on n side by the same formula. Now we study the p-n junction through the energy band diagram. So this we have seen how the band bending takes place. Band bending takes place across the depletion layer. This we have already proved that the energy profile of electron, potential energy profile of electron across the depletion layer will be like this. On the left hand side, we will have the conduction band of p side, and on the right side, we have the conduction band of n side. And you see, under thermal equilibrium, when we have not connected our p-n junction to the external battery, we have only one Fermi function. This is the definition of any equilibrium. Under equilibrium, we will not have two Fermi functions, rather we will have only one Fermi function. That's why the difference of Fermi energy would be equal to 0. On n side, we have large number of holes. On p side, we have large number of holes. On n side, we have large number of electrons. But these electrons cannot go from n side to p side because of this potential energy barrier, which is equal to EV0 in terms of potential energy barrier. Similarly, these holes cannot go from p side to n side because of the same amount of potential barrier they feel. But when we connect our device to the external battery, which is known as forward bias, positive terminal is connected with P, negative terminal is connected with N. So this built-in potential will get reduced by the amount EV0 minus V. Now this built-in potential has decreased. These electrons now can easily diffuse from N side to P side, and because their number is very large, so we will get a significant amount of current. Similarly, these holes can diffuse from n side, from p side to n side, and now you see we have disturbed the equilibrium. That's why we will have two Fermi function. The Fermi function on n side moves up, the Fermi function on p side moves down, and the difference is EV. If we connect it under reverse bias, the strength of built-in potential will be increased by an amount EVR. So now the potential barrier height seen by these electrons on n side and holes on p side will be EV0 plus VR. So these electrons cannot go from this n side to p side, which are majority carriers, and holes cannot go from p side to n side. So we will not get any current due to diffusion, but because this electric field is very high, if they will break the bond inside the depletion layer and electron hole will be generated, and you see the total electric field is pointing in this direction. So this electron will move in the opposite direction of electric field, and the hole will move in the direction of electric field. But these generation of electron hole pair is, and their motion is due to the drift. Diffusion current is 0 under reverse bias. Only very small current will be due to the drift of minority carriers. So let me summarize it. Under forward bias, we will have the diffusion current dominating the overall current. Under reverse bias, diffusion current will be small. Only we will have small amount of drift current. So this is how we plot the So we have this characteristics, IV characteristics of the semiconductor, in which the total current is diffusion minus drift current. This equation is known as the Shockley equation. The derivation is given in many books. I is equal to I naught e to the power EV upon kBT minus 1. Sometimes we will also have a factor of eta here. Eta is known as ideality factor. It tells us how good or how much ideal our semiconductor is. So you can see that under forward bias, this exponential term will be positive and it will be much, much greater than 1. That's why you see the variation is exponential. The current increases exponentially. With a very small increase in current, with a small increase in voltage, current increases drastically. Under reverse bias, this term will be negative, very small compared to 1. We will have only very small current, that is reverse saturation current, I know, very small current, unless we reach the breakdown region. So this is all about forward bias and reverse bias. This graph shows that when we connect the semiconductor with forward bias, so we will have how the electron concentration will change due to this biasing on the n side, and the hole concentration will change on the n side, because this area represents the hole diffusion which are diffusing from p side to n side, and similarly the electrons which are diffusing from n side to p side is shown by this curve. The depletion layer width under forward bias gets reduced. In reverse bias, it increases with respect to the thermal equilibrium value. So these are the references for this, and with this, I think I have discussed what I wanted to discuss.